there, swarmers! Welcome back to the Hive. Today, we are talking plastic. Some facts. If you didn't know, plastic is made from petroleum. About 8.3 billion tons of plastic has been produced since the 1950s, which is roughly the weight of a billion elephants or 47 million blue whales. And only about 9% of that plastic has ever been recycled. 12% has been burned, and the remaining 79% has ended up in landfills or in the environment. Plastic pollution is the most widespread problem affecting our marine environments. It threatens ocean health, food safety and quality, human health, coastal tourism, and contributes to climate change. The good news is, innovative new science is fighting to figure out a way to deal with all of the plastic pollution currently in our environment and to prevent more from ending up there. So today, we're here with Trévon Gordon. He is the founder and CEO of Vader Nanotechnologies, a company doing amazing work in the science and environmental space. Their project, Green Quorum, is creating enzymes and organisms to literally eat plastic pollution. So hi, Trévon, welcome, and thanks so much for being here with us.
Thank you so much, Lexi. It's a pleasure to be here. That was an awesome intro and an awesome, overview of the plastic pollution problem. So yeah, that was perfect. Thank you.
I'm glad you think so. Thank you for the amazing work you're doing. I can't wait to learn more about it.
Yeah, I'm excited to share with you guys.
Let's start with, why don't you tell us a little bit about yourself and how you got into the incredible work that you're doing now?
Yeah, so my background is in biochemistry and chemical engineering. And originally when I I chose that track for myself, it was to kind of work in the biomedical sciences because my interest is actually, it originally was actually interested in autoimmune diseases because I have an autoimmune disease. A lot of my friends and family have autoimmune diseases. And so my goal was to use this understanding of biochemistry and chemical engineering to apply that knowledge ultimately and treat these autoimmune diseases. But I ultimately, as I was working on this problem, met a few people who were working in this space in terms of, reducing single-use plastics and other innovative solutions. And at the time I was working on a project related to drug delivery, basically tolerogenic nanoparticles, and they're made of polymers, essentially, the same way that plastic is made of polymers. And my understanding about the biodegradability of those nanoparticles kind of provided some crossover with the understanding about plastics and how we could potentially make plastic biodegradable. Basically, when I finally took my startup seriously, roughly last summer, and I came to this community lab called GenSpace, my goal was to train organisms to eat PET plastic, which was already demonstrated in the literature to be possible. My goal was to use those organisms that eat PET plastic for another purpose. But because I didn't want to spend the time and the money in basically the genetic engineering necessary to, get these organisms to eat PET plastic, I was thinking about how can I do it, in a different way using my understanding of biochemistry and chemical engineering. And so the approach I took was, can we just train organisms to eat PET plastic? And as I was kind of like moving down this direction with research, I started to meet a few other companies in this space who, were interested in, let's say, bioremediation solutions for landfill problems and things like that. And as I started to learn more about this space, I started to realize that the real awesome thing that I'm developing isn't the organisms that eat plastic to do X, eat PET plastic to do X. It's how to train organisms to eat plastic. And so that's when we kind of focused in on how can we create a platform to develop organisms to break down plastic, many different kinds of plastic, not just PET plastic, but polyethylene, PVC, etc. So that's the journey.
That is so crazy cool. I'm so excited to learn more about that. That's really amazing. So you kind of just mentioned it, but before we get into more details of the intricate work that you're doing, there are literally thousands of different types of plastic, right? Each with their own composition and characteristics. So again, you just mentioned it a little bit, but what types of plastics are you working with and how did you come to select those plastics?
Yeah, absolutely. So we started working with polyethylene terephthalate (PET) plastic, but then as we kind of began developing the platform more, we realized because the organisms that break down and eat polyethylene terephthalate (PET), they already exist. So our focus instead shifted to polyethylene. So we know a few organizations who've already started the process of developing chemical processes to break down polyethylene and recycle polyethylene. So I was essentially, my interest was, can we create an enzyme similar to PET similar to the enzyme that breaks down PET, PETase, can we create an enzyme for polyethylene that does a similar function? So now we've shifted our focus. We are a small startup, so our focus is only for polyethylene right now in terms of plastics. I saw a few articles around polyurethane. They discovered a new organism that breaks down and eats polyurethane. So I'm excited to work in that space as well with polyurethane soon. But right now we're solely focused on polyethylene. And then also in terms of PFAS chemicals, that's another focus for our startup. We're working with a chemical called PFNA, or I think it's polyfluorononoic acid, is the full chemical name, if anybody out there wanted to look it up. Yeah, so those two, polyethylene and PFNA, are our two focuses, and yeah.
Great. So, okay, so now we know what types of plastics you're working with. Can you explain what types of enzymes and organisms you're working with and what that selection process is like?
Yeah, so we're actually working with E. coli exclusively right now, but there's so much opportunity in terms of selecting new starter organisms. We're seeing a few different organisms isolated by a group at Princeton that have the ability to completely break down and defluorinate PFAS chemicals. And Pseudomonas in general seems like a really great starter strain for directed evolution for plastic and for PFAS. So we want to head in that direction with using some of those other strains, but right now just E. coli. And in terms of the enzymes, so the process actually starts the same for both. So instead of let's say developing just the enzyme, you just develop the organism, right, that can eat plastic. So a little bit more info on our process is, as we train these organisms to eat plastic as a carbon source, they're naturally developing those enzymes to efficiently break down plastic and use it as a food source.
Mm.
And so when you're training the organism, you're actually also optimizing the enzymes as well. So yeah, E. coli, and then we'd have to do the studies, the metabolic work, to understand what enzymes inside of these organisms are able to break down plastic. But yeah.
That makes sense. That makes sense. It's like our bodies, right? Like we just are developing tools to break down the things that we're putting into our bodies.
Exactly, 100%. And on that note, I mean, I'm sure you know this, but like plastic is one of those things that are slowly working their way up into our food and essentially into our bodies. So yeah, the idea is the same, and sadly, unfortunately, plastic kind of goes into that kind of umbrella of things that we're breaking down, but or
Yeah.
trying to break down. But
Yeah. So, can you give us some examples of these types of plastics, your polyethylene and the PFAS that you're talking about? Just so, like, I'm trying to envision these little guys like eating this plastic and these chemicals, and I just want to have an idea of like what will I know in my daily life as that type of plastic?
yeah, so for examples of polyethylene, that would be things like your shampoo bottle, or the plastic bag packaging for your hot dogs, or you know uh, some other disinfectant container that you might be using, or disinfecting bottle. Most of those cleaning bottles are made of polyethylene. PFAS it's found in fire extinguishers. It used to be found in the nonstick pans for nonstick cooking,
Yeah.
and a few other things.
Thank you for that. That's helpful for us non-engineer brains to be able to know, like, okay, that's what that is. That's what we're talking about. Appreciate it. So, how do you mentioned training the organisms, and I think I saw on your website you mentioned directed evolution techniques.
Yeah.
What does that look like? Like, how do you train an organism?
Oh yeah, I'm super excited to show you guys the process that we've been working on. So essentially, and this is where we've got it as of like last week, 2 weeks ago. We use image analysis to select organisms that grow. So essentially, most organisms that we you know select for the assay to whether or not they grow, most of them don't grow. Most of them aren't able to use plastic as a carbon source. I should explain first of all what the assay is, right? So the assay that we've developed is basically it uses something called minimal media. Minimal media contains all of the nutrients for cells to grow minus the carbon source. So they have a nitrogen source, they have all of these other trace salts that are important for cell growth, but they don't have a carbon source. And so what we do is we supplement that media with the carbon source of interest. So if that's plastic, we'll put plastic in the media. If that's PFAS, then we'll put a PFAS chemical in the media at reasonable concentrations not to kill the cells. And then essentially what we're doing is we're using image analysis software to carefully monitor each of these experiments and see what cells do grow. And when cells do grow and they're able to use plastic as a carbon source, that's our indication that they're breaking down plastic.
Hmm.
So that's our readout for this assay. And then we follow up with, like we spoke about before, the metabolic studies to understand how that process is actually happening. But the start of training the organisms happens by selecting or using image analysis to select and monitor cells that have the ability to break down plastic.
Wow. This is so cool. I'm just learning so much. What you're doing is like really amazing, so revolutionary.
Thank you.
How long do you think this will take for this to be scalable and like in our world?
Yeah, I think I love that question too, because that's a question that is like top of my mind as somebody who's doing this development.
Sure.
I think 2 years for plastic, right? For isolate or for selecting a few organisms with the ability to break down polyethylene plastic, and then doing the metabolic studies to understand the enzymes responsible for that polyethylene degradation. Then we're at a spot where we can think about how can we commercialize these enzymes or these organisms, and open that door for further optimization, whether it be through our platform or through other methods that exist and are common in biotechnology. But that's kind of the timeline that I'm thinking of, roughly 2 years, to kind of hit that mark. I think PFAS is sooner. Um, with developing organisms that eat PFAS, the hurdle there is not the enzymes, but actually the regulation around deploying organisms for bioremediation.
Hmm. What does this look like in our daily lives? Like, would it be its own separate facility, or could it be these plastic eating or forever chemical eating organisms be integrated into landfills and the ocean? What are you thinking?
So we are a contract research organization. So it's definitely going to be a third party chemical recycling facility. These would be the companies who already have some sort of process already up and running that might not be extremely efficient based on their current methods. The goal of developing the enzymes is to basically increase efficiency, reduce the energy needed to break down these chemicals, so that they can ultimately reduce the cost associated with recycling. So it would look like us partnering or operating as a contract research organization with those chemical recycling companies, so that we can help them do their job better.
Hmm.
And that's kind of how we generate revenue.
You kind of answered it, like if it could be integrated right in landfills and other third-party things, but
Yes.
really like ocean gyre garbage patches and stuff like that.
Okay, I definitely wanted to touch on the idea around deploying organisms to break down plastic in landfills or in the ocean, which I think whenever we stumble into this space with plastic and potentially organisms that can break down plastic, I noticed like a lot of attention immediately goes to, can we deploy this in a landfill, like deploy the organisms themselves in a landfill, or can we deploy this in the ocean to break down microplastics, let's say? And unfortunately, or maybe fortunately, depending on how you look at it, that's probably not the best way to go about it, because it comes with a lot of complications. We don't know what happens to those organisms once we deploy them in the environment. There's a lot of risk around that. was also a lot of regulation around deploying genetically modified organisms into the environment. So when it comes to deploying in landfills, it's probably not the approach that we'll take or won't be able to take for a long time. Based on what we know around PFAS and deploying organisms to break down PFAS, we need to be able to have some sort of readout to measure the effectiveness of deploying these organisms. Right now for plastics, in terms of as a bioremediation target, there's really nobody developing those metrics to understand how we can, deploy some sort of bioaugmentation approach for breaking down plastic in landfills. And just by extension, that would also go for the ocean as well.
Yeah, well, it's good to hear that you're doing this so consciously, right? Because you don't want to create more problems by solving another problem.
Exactly.
What are your thoughts on the future of plastic production? I mean, like in a dream world, we just stop using plastic forever and ever. But what do you think about the future of this?
Wow, big questions. Okay. So I think like exactly like you said, like ideally we're not using bioplastic. We're using bioplastics for everything, and everything is biodegradable, and we can kind of just completely cold turkey cut plastics out in their usual form. But there are, and we kind of hinted at it before at the beginning, there are thousands of kinds of plastics, and they all have a unique use or purpose. And it's because of the versatility of plastic that we use it in so many different ways. Bioplastics are super interesting and are useful in many different scenarios, but they're, in terms of having that versatility that plastic currently does, it's really not, it's not on the same level just yet. And there are things that we just still need plastic for. I think rather than trying to develop a substitute for every single kind of plastic, which is really difficult, what I think the approach that we currently have allows us to do is develop a method to break down every single kind of plastic. And that's really what our goal is if we start with the most difficult plastic and we slowly, one by one are able to tackle other plastics with the same approach, then we can get to a place where even though we don't have the best alternative just yet, at least we can reasonably break down, degrade, recycle these plastics, in an environmentally friendly manner.
So lastly, if you had one tip, your like favorite tip, or piece of actionable advice for dealing with plastic in our daily lives, what would that be?
Yeah, I love this question. So we have this thing at GenSpace called Member on Socials, where we pick a different topic and we talk about it. And the one that I led maybe about 2 months ago was about plastic. And we threw up a poll basically of different things that we can do to address the plastic pollution problem. And one thing that I noticed from some of the members is that being able to completely phase plastic out of your life is really difficult. It's just not feasible for some people because plastic saves a lot of money for a lot of different people. And if you're living somewhere where you're just getting by and things are difficult, sometimes you can't afford to be able to phase that out. We talked about plastic bottles. I know plastic bottles are pretty huge in terms of their contribution to the plastic waste problem. I think one thing that we might be able to do, that one member suggested and that the group kind of agreed on, is to learn how to effectively recycle. It's not an easy task by any means. It's a very complicated, at least for some, it can be very complicated to know what to do with the different waste that you're generating. If you could, or if you want to participate and to be able to help, just knowing and taking the time to, get the knowledge to on how to recycle, I think maybe is a reasonable start. Because again, if you can't not use plastic bottles. And some of us, we don't have the ability to do that. If you can't, then if you want to participate, then just figuring out how to effectively recycle and to put your waste in the appropriate bins is a huge step.
Yeah.
It seems so small, but just knowledge can be incredibly impactful. So that would be my little bit of actionable advice.
I think that's awesome. It's so true. Knowledge is power, right?
Exactly. Yeah.
And shameless plug, we have some videos on how to properly recycle. So,
Hey,
wow, check them
that's perfect.
out. Thank you so much, Trayvon. I learned so much. I'm sure our viewers did too. This is really fascinating stuff and important work you're doing. So thank you for the work you're doing on behalf of our planet. We love it.
Thank you. It's been a pleasure to be on here and to speak with you. You have an awesome platform. The work you guys are doing is also incredibly impactful. As we just said, knowledge is power. You guys are spreading lots of knowledge, and you guys are doing it in a really wonderful way. So yeah, thank you.
Thank you. We're in this together, right? All of us in
Absolutely.
this together. I love it. Thanks so much.
Absolutely.
Thanks for joining us, swarmers. Don't forget to like, share, and subscribe, and we will see you next time.